Good evening, everybody. I am Vibhu Swain from Power Tech Consultant. Today we'll start our webinar number 31. Let me share my screen with you all. So in webinar number 31, we'll discuss about furnace, which is basically chapter 4 of book 2, that is energy efficiency in thermal utilities. Now, as you all know, furnace is basically a very important equipment in any steel plant or any aluminum plant or any copper plant. So any ferrous, non-ferrous type of metal industries, furnace is a very important equipment and it consumes a lot of thermal energy. So energy saving point of view, furnace also plays a critical role. And as an energy auditor, we all have to know how to conserve energy in any furnace application. Before that, we need to understand what exactly a furnace is. Now, basically, the furnace is an equipment to melt metals for casting or heat materials for change of shape, rolling, forging, or change of properties. That means we need to make good steel, so we need to reheat it and cool it down naturally. That is basically heat treatment is given to any metal to increase its properties. Another one is we get billet from continuous caster or slab from continuous caster in a steel plant after the SMS. But need we need to obtain flat plate angles rods. So we need to roll the product for which a heat treatment has to be given to change the shape. That means it has the material has to be rolled, forged, for which its temperature has to be increased. It has to be we make into molten form so that we can really forge it or roll it. Now this thing is done in an furnace, which basically melt it or heat the material so that we can change the shape of the materials of steels and aluminum, whatever. Now, what are the different types of and classification of different type of furnaces? This is an important question. In each year, we get one question, may it be a long question from furnace. Now, based on generating heat, furnaces are broadly classified into two types. One is combustion type, another one is electric type. That means if you are using fuels, then it will be a combustion type. But if you are using electrical energy, then it will be electric type. Now, combustion type furnace can be oil fed, coal fed, or gas fed. But electrical type furnace is basically resistance types or induction heating type or arc heating type. There is also a submerged arc furnace, which is normally utilized in producing ferrochrome, particularly found common in Odisha, where chromatora very much is there. So, in submerged arc furnace is basically an arc furnace in which arcing is then take place in submerged conditions. Then induction furnace is basically utilized in number of mini steel plant, and we have oil fired and gas fired furnace also for reheating the feed material. Apart from that, furnace classification can be broadly described in this picture. First one is according to mode of heat transfer. Second one is according to mode of charging. Third one is according to mode of heat recovery. Now, if you are hiring in an open place or there is the heat transfer is occurring in an open furnace, then it will be treated as open fireplace furnace. If heat transfer is done through a medium, then heated through medium type of furnace. Then according to mode of charging of the feed material or the stock, which needs to be reheated. One is batch type, another one is continuous type. In batch type, there are three types: forging, re-rolling, or continuous Pulsar type, pot type. In continuous glass stack melting, you have continuous regenerative type also, it's a continuous. Now recuperative or regenerative, that means how you can utilize the waste heat. Based on that, heat recovery medium also furnaces are classified. So basically 3 level of classifications, and classification is open fire, heated through medium, batch, continuous, recuperative, and regenerative. Now let us understand the characteristics of an efficient furnace. Now furnace should be designed basically, which you are giving heat, and we need to heat the material as much we can so that a uniform temperature is attained, and possibly with less fuel and labor. Then we can tell that furnace is efficient. That means these 4 parameters are required to be studied so that to understand the efficiency of furnace. One is determination of quantity of heat to be imparted to the material or charge. How much of heat is required to make it into molten stage or to make it reheated so that the further processing can be easier. The second one is liberation of sufficient heat within the furnace to heat the stock, overcome all heat losses. Now, heat losses is very important, and lot of heat is lost in a furnace. So we need to overcome that heat loss. Then transfer of available part of heat from furnace goes to surface to the heating the stock. The third one is equalization of temperature within the stock. We need to see that the heating is efficient so that the temperature of the stock or the material which is being heated is uniform throughout its surface or throughout its body. Then reduction of heat loss. Heat loss should be minimum. So these are the major parameters of or characteristics of an efficient furnace. Next is furnace energy supply. Now, what type of energy we can supply to a furnace? Whether it is coal energy, what is it, gaseous energy, or liquid energy? Particularly when you use coal, normally it contains sulfur, due to which it may affect the feed material, the quality of materials. Also, if you use coal, it may give rise to ash or solid fuel particulate (SPM). So it may change the quality. So normally coal is not used. So what is left? Liquid fuel is used, gaseous fuel is used, or electricity is also used as a major fuel for the furnace. Now, electricity is used in induction and arc furnace for melting steel and cast iron. Non-ferrous melting normally utilize oil as fuel. So these are the two major energy supply source for any furnace. And as you know, these are very important and there are very priced fuel supply. So we need to conserve those fuel supplies. Now let us come to an oil-fired furnace. Now, in this case, what is furnace oil is the major fuel, and sometimes we use LDOs because the sulfur presence is, we don't want sulfur change the characteristics of the feedstock or the charge material. So this oil is basically used for reheating and heat treatment of the materials. Now remember, the furnace efficiency is very low. Maybe it may be 7%, it may be 20% max, or maximum 40%, depending upon the size and the feedstock what you are utilizing. But if you see, normally a boiler or the steam generating devices, the efficiency can be in the range of 80 to 90%. Now, why furnace efficiency is low in that case? Because furnace operates at a very high temperature to melt or heat the stock. That means we require minimum 1200 degrees centigrade to melt any metals, particularly iron and steel. That means when you heat the temperature of 1200 degrees centigrade, so lot of exhaust gas leaves at 1200 degrees centigrade. Now this is a huge heat loss. Now unless you don't employ any regenerative or reheat recovery technologies, then the furnace efficiency has to be low. Now also we need to control the excess air because furnace you have lot of opening to uh, to make entry the feed materials, and while taking out the charged material or hot material you need to open the gate. So also there is a huge heat loss due to opening, and we need to control excess air as well. Now if you can preheat the stock or combustion air, or you can get waste heat recovery systems employed in the furnace, then furnace efficiency can be improved. Now let us understand typical furnace systems. One is forging furnace. Now forging furnace is basically used for preheating billets ingot to attain a forged temperatures. Normally this forging furnace operates at 1200 to 1250 degrees centigrade, and it is an open fireplace systems. Now most of the heat is transmitted by radiations. Now, in case of any furnace, there are the operating cycle consists of three time zone. One is heat up time zone, soaking time zone, and forging time zone. So these are the operating cycle of any forging furnace. We need to heat the material. Then the material the heat need to be soaked, so it will attain uniform temperature. Then there you need to forge. Sometimes you have to reheat the materials. Remember the forging temperature is around 1200 to 1250 degrees centigrade in case of forging furnace. Now this is a picture of forging furnace. Now here you are feeding in the materials and fuel supply is given here. This is burning. Now normally large peaks are soaked for 4 to 6 hours inside the furnace to attain uniform temperature throughout the cross section of the material. Now, the soaking time may differs. It depends on the type of materials. It depends on the thickness of the materials. Now, if the material is very bulkier, then what will happen? You require lot of energy to heat the materials, and largest piece may have to be reheated several times. Now, the charging and discharging of the material is done manually. So, since there is a manual charging and discharging, there is a significant heat loss occurs during forging operations. Forging operation, as I told, open fireplace, it utilizes open fireplace system. So most of the heat is transmitted through radiation only. Now, specific fuel consumptions depend upon the type of material, number of heat requires. Now, if the material is changed, why? Because the specific heat of the materials also get changed. So, based on the specific heat of the materials, your specific fuel consumption differs, and also thickness, also number of heat required, the reheat requires also decide the amount of fuel required for any furnace. The second one is re-rolling mill furnace. Now it has of two types. One is batch type, another is continuous Pulsar types. Now in case of batch type, it is basically box type furnace, and these normally hits up scrap, small ingots, billets, and normal weight of these products is 2 to 20 kg, and operating temperature is basically 1200 degrees centigrade. Now here we charge this billet and we get the final product in terms of rod, angles, channels, strips. So basically, it is a normal re-rolling furnace in case of any mini steel plant. Now the total cycle time can be further categorized as heat up time and re-rolling times, because while re-rolling, we need to treat the material also sometimes, and heat up times. Now during heat up time, the material gas gets heated up to required temperature and is removed manually for re-rolling. The average output is normally 10 to 15 ton per day. That means the batch type you can have a smaller capacity 10 to 15 ton per day. But whereas in terms of continuous Pulsar type, the capacity of product handling can increase up to 20 to 25 ton per day. Now the process flow operating cycles of continuous Pulsar type is same that of blast furnace. Now this material or stock records the part of heat in flue gas as it moves down the length of the furnace. In this case, what happens? The charge moves. Now it can move due to pushing of the charge, so that in one end during the discharge end, heat is burner throws the heat into the charge, and the charge moves and the gases moves in the opposite direction, which feeds the entry charge, and the exit charge is heated with the burner, and you get uniform temperatures. The heat absorption by the material in the furnace is slow, steady, and uniform throughout the cross section compared to blast type. So here we can get a steady uniform because this is a Pulsar type in which continuous heating is carried out. So this furnace normally operates 8 to 10 hours with an output of 20 to 25 ton per day. Now this is a continuous steel reheating furnace. Here in the case of reheating furnace, the steel is typically heated between 900 degrees centigrade to 1250 degrees centigrade until it is plastic enough to be placed or rolled to desired section, size, or shapes. That means in this case we change the size and shape of the steel. The furnace must meet specific requirement objective in terms of stock heating rates for metallurgical and productive region. Now, if you see, it is a continuous reheating. The steel stock form a continuous flow of material and is heated the desired temperature as it travels through the furnace. Now, this is a typical example of reheating furnace. You see, this is a charge door. The door is opened. This is a material which needs to be heated. The material goes like this, and there is a pushing mechanism occurs. Now, this is a stock that moves. Sometimes the hearth moves, or sometimes the stock can also move. There are different technology how the stock or hearth can move. Now, this is a burner in which fuel is supplied, and there is a burning zone, and this is basically a soaking zone, and in which the discharge door opens, and the material once heated up goes for further processing. Now you see here, this burner here, the size is basically the height of the furnace is high, whereas in this place the height is little bit lower because this is a burning zone, and you require some air for this, and this is a furnace chamber. This is the path of exit flue gas. Now, if you see heat transfer in the furnace, this is a stock, this is a flame. Now, there is a radiation from the flame, there is a radiation from the combustion products. The combustion products surrounds the steel stock. So there is a radiation from that, flame radiations, and from the wall is also heated up. There is a refractory is placed for the wall, and due to which the wall also radiates. And because also the excess air or the dry flue gas travels in the medium, so there is a convection heat transfer also occurs from the dry flue gas to the steel stock. So these are the furnace heat transfer medium in the furnace. One is radiation due to flame, radiation due to combustion products, radiation due to wall of the furnace, and the fourth one is convection due to the circulating dry flue gas. Now, what are the major features of a reheating furnace? Normally, as I told you, you need to reduce the heat loss. So there is a refractory chamber constructed of insulating materials so that it can retain heat at the high operating temperature zone. So we need to place some refractory, and it acts as a insulation, and it avoids the wall loss or heat loss to the wall. Then there is a hearth to support or carry the steel. That means The hearth is basically the bottom portions of the furnace, and it is consist of refractory materials. It and there is some metallic supports has to be provided, and it has to be water cooled because it is exposed to very high heat in zone, so it needs to be cooled continuously. So the furnace hearth is water cooled. Burner is also another systems that use liquid or gaseous fuel to raise or maintain the temperature in the chamber. Coal or electricity normally can be used also, but for reheating, now there is a method to remove the combustion exhaust gas through the chimney. Then there should be some method for introducing the steel into the chamber, and there should be some method to take away the heated material from the chamber. So based on the size and shape of the steel to be processed, the size and type of furnace is also different. And based on the general layout of the rolling mill, the size and type of furnace has to be different. Now, the common system also include roller table, conveyor, charging machine, furnace pushers. So these are the major important features, characteristics of a reheating furnace. Now, the major components are refractory, burner, then tables, hearth, roller tables, conveyor, charging machine, and furnace pusher. As I told you, the heat transfer in furnace occurs two types. One is radiation from the flame, hot combustion products, and the furnace wall and roofs. Also, convection due to movement of hot gas over the top surface. Now, as the high temperature employed in heating furnace, dominant mode of heat transfer is wall radiations. Normally, the radiation from the wall is the major heat transfer source. Now, heat transfer by gas radiation depends upon the gas compositions, mainly carbon dioxide and water vapor, the temperature and geometry of the furnace. So, this is the heat transfer in furnace. Now, let us understand types of continuous reheating furnace. Now, continuous reheating furnace are primarily categorized by method in which stock is transported to the furnace. There are two basic methods. The continuous reheating furnace, one is pusher type furnace, another one is moving hearth or supporting structure which transport the steel through the furnace. So, based on how you are moving the material inside the furnace, based on that, there are two types of continuous reheating furnace. In one type, you push the material from charging end to discharging end, and that will be treated as pusher type furnace. Now, in second case, you employ some supporting structure or some moving element or moving earth in the furnace, which will move the material inside the furnace. So, based on these two broad category, furnace can be divided. So, walking beam, walking hearth, rotary hearth, and continuous recirculating bogey furnace. Out of which walking beam is important, and it is employed in thermal steel plant, and this is a very efficient furnace. We'll study about all these furnace. Now, basic, as I told you, basic philosophy is now the inlet and outlet aperture should be minimum in size and designed to avoid air filtration to increase the efficiency of the furnace. Now, see here, in case of pusher type furnace, what happens? Now, this is a discharging end, this is a charging end. Burner are placed here. Now, there is also a burner. In case of burner end, the height is high. In case of away from burner, the height of the furnace is low. So, there is a tapering of furnace depending upon the position of the burners. Now, this is the soaking zone. That means in soaking zone, this is a solid earth in which burner is there and in which the material, heated material is taken out. Now, this is the water cooled skid systems or supporting stock. That means there is a skid on which the material moves, and this is a charging it. This is the material or steel plate or steel slab which are to be heated up. Now, these things are pushed, butted together, and it is pushed so that you get heated material outside the discharge end. Now, it is also popular in steel industries, relatively lower installation and maintenance cost compared to moving hearth furnace, because there is no moving element is involved. The hearth is not moved, the beams are not moved, only the material get pushed and moved. Now, these skids also needs to be water cooled because it is exposed to very high heat, but it has some disadvantages like frequent damage to refractory hearth. Since this material is moving, friction is there, so skid refractory hearth is get damaged. Now, since you are water cooling the skid and stock supporting the structures, the supporting structures and skids are water cooled, so there is a energy loss due to cooling. Now, discharge must be accompanied by charge. Unless there is no charge, you cannot push the material. Once you charge it and you push it, then automatically you get the discharge material. So sometimes if charge get finishes, what will happen? There will be some material will be inside, and you cannot discharge the material, so heat loss will happen. Then stock size, weight of the and furnace length are limited by friction and possibility of stock pile-offs. All round heating of the stock is not possible since it is moving and the bottom portion cannot expose to the heat or burner. Therefore, uniform heating is not achieved. Plus, since there is a limitation in pushing the materials, so the size and weights and the furnace length is limited. You cannot have a very big furnace out of Pulsar type. Then walking hearth furnace, you can see some videos in YouTube. In case of walking hearth furnace, what happens exactly? Now, these are the moving beams. The beams are moved and there is a roller here. Now, this is a small height, this is a large height. Now, there is a motor mechanism are there. So, what will happen? And there is the support structure, fixed refractory earth. These refractory earth is fixed, and this is the stock. And these are the burners in which oil is fired. Now, when material get entered, what happens? This roller moves like this. So once you move upward, this material gets moved. Then again, it is put again it is moved downward and backward, so that material again rest and it goes come back. Now this process is repeated so that you can get, because of this hearth is moved, this hearth is moved and you get the material out in the discharge line. So by moving the hearth, you can get the material in and out. Therefore, it is known as walking hearth furnace. The hearth in this case works to move the materials so that it will be continuously heated up, and after the soaking zone it will be get discharged. Now these furnaces have several attractive features including simplicity of design, ease of construction, availability of to cater different type of stock size, and there is minimum negligible water cooling loss, and minimum physical marking of the stock. Now you don't require any minimum size because you don't have to push the stock because of walking earth. The stocks are getting in. So even if there is no charging, you can get the metal out. But here also bottom phase of the stock cannot be reheated, and the small space between individual stock pieces limit the heating side. That means there is a small size is there. Therefore, uniform heating is not possible, and stock to have uniform heating, the stock residence time has to be increased. Now, this will increase the furnace flexibilities, and this will increase the furnace loss. So, it will have some effect on the furnace flexibilities and the yield. Now, if the furnace or the material remains inside the furnace for a longer time, what will happen? Some skid loss will happen. scaling loss will happen. So there is yield will be affected. So some amount of iron loss will happen due to scaling, and these are the major disadvantage of working hearth furnace. Now, rotary hearth furnace is utilized for basically for small component to be heated up. Now, in this case, what will happen? There is a rotary system is there in which the hearth keeps on moving, and you input the material, charge the material. Now it gets heated up. The burner are placed in like this in the circular periphery. Now it moves like this at a slower speed, and you get heated materials from the exit point. So basically, rotary hearth furnace is supersede the circulating bogie type, and heating and cooling effect introduced by the bogies are limited. So heat and storage loss are less, and more complex design with annular shape and revolving hearth. So it is of in annular shape and revolving hearth. Now continuous recirculating bogie type furnace. Now in case of bogie type furnace, what happens? There is a bogie is there, like train bogie, and there is a rail is there. These are the wheels. Now the material which needs to be heated up, it's placed in the bogie. Now this is a dischargeant, this is a chargeant. Burner has placed throughout the periphery of the furnace and the wall of the furnace. Now this material gets heated up. Now the bogie goes out, again comes in. So this is a bogie, recirculating bogie type furnace. But the limitation is that here the length can be high, but the thickness of the furnace is low, or the very less. Again, some heat loss occurs because once the material is heated up, this bogie also heated up. So there is a considerable material or energy loss occurs during bogie type furnace. And the stock is placed in bogie with refractory hearth, which travels through furnace with the other in the form of train. Now, bogie furnace tend to be long and narrow and suffer from problems like inadequate sealing of the gap between bogies, furnace cell difficulties in removing the scales, difficulty in firing across the narrow hearth width. So this is a narrow hearth width is there because the bogies are placed inside it, and these are the disadvantage of recirculating bogie type furnace. Now come to walking beam furnace. This is one of the important and energy efficient furnace. Now walking beam furnace overcomes many of the problems of Pulsar furnace and permit heating of the bottom place of the stocks. This allows shorter stock heating time and furnace length, thus better control of heating rates, uniform stock discharge temperature, and operational flexibilities. In common with top and bottom fired Pulsar furnace, however, much of the furnace is below the level of mill. This may be constrained in some applications. Now, in case of walking beam furnace, what exactly happens? Now, this is a charging end. Now, these are the billet, long billet which are placed in the beam. Now, these are the beam. These are the moving beam. There is one stationary beam and another one is moving beam. Now, the cooled skid system supporting stock. So, these are cooled skid system supporting the stocks. So, these supports the stocks. Correct? These beams supports the stock. Now, these beams are walking or movable. These beams are fixed. These beams are movable. So these beams, particularly the movable beams, are connected in the bottom like this. Now, if you see, there is a roller. Now, here this roller operates on a tapered platform. So what will happen when you in a motor you move this roller like this? What will happen? This movable beam goes to the top, means height increases, so it takes all the materials, and as it moving forward, this movable beam walks and takes the stock. After that, again it comes back to original positions. While the movable beam coming back to the original position, its height gets lowered. Again, this charge or the billet so gets the support of the fixed beam. Like this, again, this beam, this movable beam again moves. So like this movable beams keeps on moving the material from one end to other end. So this is a simple mechanism of walking wing furnace. Here burners are placed. There is a tapering. In this case, the height is higher. In this case, the height of the furnace is lower. And this is a soaking zone. This is a discharge end. This is a charge end. Remember, there are fixed beam and the walking beams. So walking beam is normally moving the stock due to tapered movement of the um, this mechanism which is placed below the furnace. Now the sixth one is Copula Furnace. In this furnace, what is happens? This is basically cylindrical type of furnace. Now in this furnace, it is mainly utilized in case of foundry to melt pig iron, cast iron, foundry returns. Now the chart is in the used in the Copula furnace is basically consists of alternate layer of coke, flux, and metal iron. Now see here is the refractory lining. Now this is the metal. This side is metal, and this is the flux, and coke is this one are coke. So layers of material is charged. First coke, then metals, then flux, so that to have a uniform layers. Now flux can be limestone, fluorspar, sodium carbonate, or calcium bicarbonate. Normally limestone is normally used. Now the total weight of flux is normally 1/5 of the weight of the coke. Remember this ratio. Flux weight is normally 1/5 of the weight of the coke, whereas the iron to coke ratio is 8:1. So iron is 8, coke is 1. So based on these two ratios, these materials are charged. Now sufficient air, these are the pairs in which air is passed, hot air is thrown to the Copula furnace. Now these are the wind box, and normally it works on the counter current principles. That means the charge moves downwards, hot air moves upward, due to which the material get preheated, melts, and combustion happens, and you get molten materials. The first one is you get molten material here, and there is a slag. These are the slag which is taken out. Normally, slag is lighter than the molten metal. Metal is heavier, and from the tapping, you get the molten metals. So these are the prop bar, and these are the sand bottom or silica sand. These are the hinge to for moving the tapping, and there is a leg is also there. So this is the example or the picture of Copula furnace. In this case, what are the zones? One is preheating zones, another one is melting zones, another is reducing zone and combustion zones, and another is oil zone. In what happens exactly in combustion zone, when you give hot gas, CO is there, coke is there, so you get carbon, you get uh, the coke burns, and because of this coke burning, you get CO and you get lot of heat, and which will melt the iron materials, and because of this melting, you get again CO2, and this hot gas breathes the feed materials and goes out. So basically, there is a preheating zone, melting zone, and reduction happens in the coke conversions happens. The carbon and CO2 we get from this region. So there is a reducing zone also occurs, and combustion zone. So once you get the material goes like this, hot gas goes into the top, and you get molten metal and you get slag. slag is taken out and molten metal is taken out at the bottom. So this is that picture of Copula furnace. The seventh one is induction furnace. Now, normally induction furnace are two types. One is coreless or channel. Now, principle are same. Basically, induction furnace are ideal for melting or allowing wide variety of materials with minimum melt losses. However, little refining of metal is possible. Here, refining cannot be possible, but you can melt loss will be minimum. So, what exactly happens? Now, this is basically a primary coil. This there is no core inside it. Refractor is placed between it. Now, this is a crucible. Now, you put scrap or the material to be melted or to be melted. Then once you put the materials along with this alloy, what happens? The charge is placed. Then you apply very high induced alternating current at high frequencies. Then because of these high frequencies and electromagnetic field is created. Now, this electromagnetic field induces some eddy current or induced current in the charge. Now, because of this induction current, that induction current hits the charge, due to which the charge get melted. Now, once the charge get melted, now it also creates its own magnetic field. Now, this molten charge has its own magnetic field due to induction effect. Now, that reacts with the magnetic field of the primary side coil, and due to which some steering effect happens, which will homogenizes the melt composition and temperatures. Now, because like induction motors, motor rotor try to catch the MMF or EMF or the magnetic field of the primary supply. So, due to which motor rotates similarly, some steering also happens, which makes uniformity in temperature and material compositions. But mainly due to induction effect, the heat is charged or the material is charged or heated up and get melted. Normally, the frequency is 10,000 or 10 kilohertz. So this is basically a core loss induction furnace. Now, with this, I conclude the different types of furnace. You need to read the books to know little about Copula furnace. Also, you can see some videos on working beam type of furnace. A lot of videos are available in YouTube, so you can know easily the furnace mechanism. Normally, this is a 10 mark questions comes in the exam. What are the different type of furnace and what are the furnace classifications? With this, I close today. Good night.